Hello everyone, this is a video lecture in the subject of structural mechanics on the topic of combined loading. This presentation is created and voiced over by me, Jeremiah Dwight. To understand combined loading, we first have to understand the different types of stress that exist. There are two types of stress, normal stress and shear. We'll first start with the normal stress, which has two causes. The first cause of normal stress is tension. I can represent tension by if I take a beam and subject it to an axial force of magnitude n. The normal stress caused by n is given by sigma equals n over a, where a is the cross-sectional area of that beam. The second cause of normal stress is a bending moment. If I take a beam and instead of an axial force I put a bending moment on it of magnitude m, it will bend into a U shape like this, and the stress at any point in the beam will be given by sigma equals my over I, where m is the magnitude of the bending moment, y is the vertical distance of the point from the centroid of the cross-section, and I is the moment of inertia of that cross-section. The other type of stress is shear stress, which also has two causes. The first is torsion. So if I take a beam and this time I subject it to two torques that are represented by double-headed arrows, the direction of the twisting is given by the right-hand rule, where your thumb goes in the direction of the double-headed arrow. Those torques have a magnitude T, and the shear stress caused by those torques is given by T rho over J, where rho is the radial distance of the point from the centroid of the cross-section, and J is the polar moment of inertia of the cross-section. The final cause of shear stress is a shear force of magnitude V, and the stress caused by that shear force is given by tau equals VQ over IT, and we'll get into exactly what those mean later because it's a bit more complicated than the rest. So combined loading follows naturally from these separate types of stress in that it's just any sort of combination of those different types. It can be simply a normal stress and a shear stress, or a normal force and a shear force. It can be a bending moment and a normal force. Any combination will work. In this lecture we'll examine an example that has all four types just so that we are clear on how each type causes stress. So my total normal stress then will be a sum of the stress caused by the normal force, n over a, plus the stress caused by my bending moment, my over I, and my shear stress similarly will be a sum of the shear stress caused by the torque, that should be rho, T rho over J, plus the shear stress caused by my shear force, VQ over IT. Those are the two fundamental equations of combined loading, and that's just about the basis of what you need to know. In many cases, in most cases actually, it's not quite as simple as simply adding the two types of stress together for normal and shear, because sign matters. If we look at this example here where we've got a rectangular cross-section subjected to a normal force along its axial direction and a bending moment in the x direction, we'll see that at point A, the normal force exhibits a positive tensile stress on point A, and it does the same at point B. However, the bending moment, because of the right-hand rule, will exert a positive tensile stress at point A, but it will exert a negative compressive stress at point B. Therefore, instead of simply adding them together, at point A we can do just that, because they're both in the same direction. We've got positive tensile force from the normal direction, or from the normal force, and a positive tensile moment from the positive tensile stress from the bending moment. Whereas at point B, we've got a positive tensile stress from the normal force, and oops, that mistake is the one that I'm trying to ward you against. You can't just add them together. Instead, you subtract them because the bending moment has a negative compressive force instead. So as we can see here, we actually get two different values of stress at point A and point B. Once we figure out what the normal and the shear stress are at a given point, we like to represent that stress state by drawing it on a differential volume element. In many cases, we'll have a 3D stress state, which can be represented by a cube, where you've got some normal stress sigma, putting it in tension, and shear stress, putting it in shear. And of course, these arrows are drawn such that we put everything in equilibrium so that the cube isn't shifting at all. In many cases, such as this stress state you'll see here, there's actually nothing happening on the front face or on the back face. So what we can do is, instead of drawing a cube, we can represent it as a square and draw it as a 2D stress state instead, where I put my square in normal stress tension like that, and shear stress like so. You can't do this all the time because sometimes you will have a stress state where things are happening on all surfaces of the cube. But in the cases where nothing's happening on two surfaces, you can usually represent that in 2D instead of 3D. Now we'll look at an example to better illustrate the effects of combined loading. As you can see here, I've got a beam that kind of bends through all different axes in multiple directions. I'm subjecting it to three forces. There's P1 equals negative 50 newtons, and that's in the negative z direction. P2 equals 2,000 newtons, that's in the positive y direction. And a moment, M1 equals 100 newton meters, and that's in the positive z direction from our right hand rule. And what we're interested in is the stress state at point A here. So our objective is to determine the stress state at A and show the results on a differential volume element at that point. And just to clarify where A is, you can see from this cross-sectional diagram up here that A is on the very side of the tube, or the beam rather, and the diameter of the beam is 0.1 meters. So our first step in this whole process is to draw a free body diagram and use equilibrium equations to solve for the internal reactions at point A. So first what we're going to do is make a section cut at point A, as you can see here, and what we have left here is a free body diagram that leaves the forces on it, and I've drawn in the reaction forces at point A. You can draw them in whatever direction you want. I looked ahead and made sure that the directions I was drawing them would yield positive values for all of them. But if you draw them in different directions, you'll just get negative values instead. You'll still end up with the same ultimate result. So now we'll use our equilibrium equations to solve for those reactions. We're going to start with the sum of forces in the y direction, which is given by P2 minus Ny. Our sum of forces in the z direction gives us Vz minus P1. Our sum of moments along the x-axis gives us P1 times 0.8 meters. It's actually a mx minus P1 times 0.8 meters. Our sum of moments along the y-axis gives us P1 times 0.4 meters minus the torque along the y-axis. And our sum of moments in the z-axis gives us M1 minus Mz. Now when you end up solving those equations for the unknowns by setting them all equal to 0, since we're in equilibrium, you'll find that Ny is equal to 2,000 newtons. You find that Mx is equal to 40 Newton meters. mz is equal to 100 Newton meters. Our torque, Ty, is equal to 20 Newton meters. And last but not least, our shear in the z direction is equal to 50 newtons. So when we drew our free body diagram, we drew it such that our reaction forces were drawn on a negative surface. We don't like negative surfaces because it's harder to visualize, so what we're going to do is we're going to flip it around and draw the rest of the beam that we cut out so that our reaction forces lie on a positive surface instead. In doing that, we apply Newton's third law, which states that every reaction has an equal and opposite reaction, which basically means that since we've got the same cross-section that we cut at, we can draw all our internal reactions with the same magnitude in the opposite direction. Once we've done that, we can start to evaluate the stress caused by each of those individual reactions. So we'll start with the stress at point A, since that's what we're trying to find. And this is one of two components of normal stress, so I'm going to give it a superscript of 1. And we know that's equal to n over A. We found earlier that n was equal to 2,000 newtons, and our A, since this is a circle, is pi r squared, and r is 0.05 meters. This yields a result of 0.255 megapascals. And that is our normal stress due to the normal force. So we also want to denote whether it's tension or compression. We can do that by sign, but it's easier for us to keep track usually if we simply write tension and leave all our signs positive. If it were in compression, I would leave my sign here positive. I would just write compression instead of tension here. Next, we'll look at the normal stress caused by the bending moments. We have two bending moments, mx and mz. If we go back to our earlier free body diagram, we see that mx, the axial, the axis of mx, A actually lies on that point, which means that mx has no effect on the normal stress at point A. mz, however, does have an effect on the normal stress at point A, so that's the one we'll look at. This time we'll give it a superscript of 2, since it's the other component of our normal stress, and we know that's equal to mx times y over I. Don't be fooled by this variable. It's typically written as my over I, which is why I wrote it like that, but if you look at our axes, it's actually the direction in the z-axis. Either way, we find that it's the radius of the cross-section, so that's what we'll plug in for y. mx was 40 Newton meters. Y we said was our radius, which is 0.05 meters. We're dividing that by the moment of inertia of a circle, which is 1/4 pi r to the 4th. And that gives us a final answer for the normal stress caused by bending moment of 1.019 megapascals. And this too, by examination of our right hand rule, is in tension. Next, we're interested in our shear stress due to torsion. Just like normal stress, we found that it has two different components of that, so I will also give it a superscript. This is the first one, so it's got a superscript of 1, and we know it's equal to Ty times rho over J. In this case, A is on the outer edge of the cross-section, so rho is equal to the radius of the cross-section, r. We said that Ty was 20 Newton meters. Our radius is 0.05 meters. And our polar moment of inertia for a circle is pi halves r to the 4th. That gives us a final answer of the shear at point A, the shear stress at point A, due to torsion of 0.102 megapascals. And we also want to denote the direction. In this case, it's not tension or compression, it's simply what axis does it lie along. So in this case, it points along the negative z direction. Finally, we've got our shear stress due to the shear force. This is by far the most complicated of the four because of the variables that you use in solving for it. Earlier I said it's equal to VQ over IT. Q is what we call y bar prime times A prime. So if you take your point that you're interested in, which in this case is point A, and you draw a horizontal line at that point A across the entire cross section, the area above that is your A prime, and the centroid of that area, which is right here, the horizontal or the vertical distance from the centroid of the entire cross section is y bar prime. So in this case, it's this vertical distance right here. So we can plug those values in. I know from my cheat sheet. Oops, I'm going to use black. I know from my cheat sheet that the centroid of a semicircle is 4r over 3 pi horizontally, and my area is a semicircle, so 1/2 pi r squared. This gives us a final value of q of 2/3 r third, or cubed. So there's our q. Our t is much simpler. It's simply the thickness of the cross section at the point that you're interested in, which in this case, since A is directly to the left of the centroid, is the diameter of the circle, or 2r. So we'll start plugging everything in now. Our shear at point A, and this is the second component, is equal to Vz, which we said earlier was 50 newtons, times Q, which is 2/3 times R, 0.05 meters, cubed, all divided by the moment of inertia of the entire cross-section, 1/4 pi r to the fourth, times our thickness, which is 2r, or the diameter, which happens to be 0.10 meters. And this gives us a value of the shear due to the shear force of 0.008 megapascals. So now that we've found the stress that's caused by each individual component, we're going to find the resultant normal and shear stress by adding them together. The principle that allows us to do this is called superposition. Superposition basically just says that you can add together the results caused by each individual component to get the result caused by all the components together. You can't do this with every single property, but thankfully stress is one of the properties that you can do it with. So our first stress that was due to normal force was 0.255 megapascals, and our normal stress due to bending was 1.019 megapascals. And that gives us a final value for the normal stress at point A of 1.274 megapascals. And since both of these were in tension along the y-axis, I can add them together. If they were in opposite directions, I would have to subtract them instead. But there's our value for the normal stress at point A, and we're just going to write tension, just to be clear. The other part is the shear. Just like the normal stress, we're just going to add together our two individual components. Our first was the normal stress, or the shear stress due to torque, which was 0.102 megapascals. And then our shear stress due to shear force was 0.008 megapascals. When we add those together, we get a final value for the shear at point A of 0.110 megapascals. And just like the normal stress, we want to denote the direction of that. Again, these happen to be directed in the same direction, which was the negative z-axis. So we can just add them together instead of subtracting them. And I will again denote the direction, negative z direction. So now that we've found our stress values at point A, we want to represent that visually by drawing it on a differential volume element located at that point. So what we have to ask ourselves is this a 2D or a 3D stress state? In this case, our normal stress was directed solely along the y-axis, and our shear stress was directed solely along the z-axis. That means that there's only two states, or two directions that the stress lies along, which means we can represent it with simply a square rather than a cube. So I'm going to draw a square. I'm going to label its axes, just to be clear. And now I will draw, oops, this should be y. Now I can draw our normal stress acting along the y-axis in tension, and our shear stress acting along the z-axis in the negative direction. So at this point you might be asking yourself, well, I've got two different sides that I could be drawing the negative direction on. I could draw it on this side, or I could draw it on this side. So what we have to look at is the cube that we drew it on. Since we drew it on a positive surface, our cube right here lies just behind the cross section right here. That means that our shear, when we say it's in the negative z direction, is on the positive surface of that cube in the negative z direction. Positive surface is the positive y direction, so on the positive y direction we draw it in the negative z direction. Let's get rid of all that extraneous marking, and there we go. Each of these has a magnitude of tau, so that our square is put in perfect equilibrium. And just to remind ourselves of what that tau is, we'll have tau equals 0.110 megapascals. You'll have to forgive my coughing and wheezing, I'm a little bit under the weather. And our normal stress at point A was 1.274 megapascals. So that should give you a pretty clear picture of combined loading and how to determine the stress state at a given point based on combined loading. Just in case, I've given you a summary page here to kind of go over what we did. We said that the total normal stress at a given point was a sum of the normal stress due to normal force and normal stress due to a bending moment. And our shear stress was a sum of the shear stress due to torsion and the shear stress due to shear force. And then we can represent that graphically or visually by drawing it on a differential volume element, which could be a cube or a square depending on your stress state. And we'll draw it like this. Each of those is tau, each of these is sigma. And if you have a situation like this, which you often will unless your problem is pretty complicated, you will find that nothing's happening on two of the surfaces of the cube, in this case the front and the back surfaces, which means we can represent it instead of a cube as a two-dimensional square. And we'll just draw that same stress state on the square. And just to reiterate the steps, we start with a free body diagram, and we determine the reaction forces at the point we're looking at using equilibrium equations. Then we find the stress caused by the individual components, or the individual reaction forces there. Then we find the resultant stresses by adding those individual components together using superposition. And finally, we draw them on a differential volume element. I believe that's about it. I hope you found this very beneficial, and enjoy the rest of your day.